galaxy merger rates in the early universe were high, and this mechanism could have contributed to rapid mass growth, though models suggest it cannot account for the full required growth on its own. What Webb is doing in this domain is forcing the theoretical models to be specific. General ideas about early black hole seeding existed before Webb launched. Webb is now providing mass measurements, accretion rate indicators, and host galaxy properties for individual early quasars at a level of detail that distinguishes between theoretical possibilities rather than accommodating all of them. The early universe contained gravitational engines of a scale that restructured galaxies and altered the chemistry of vast regions of space, and they were already fully grown before our own galaxy had assembled its first disk. How they got there remains one of the most actively investigated puzzles in modern astrophysics. Point Webb at a column of gas and dust a few light years tall, and what comes back is an image of creation caught in the act. The Pillars of Creation, a structure inside the Eagle Nebula about 6,500 light-years from Earth, had been photographed before. Hubble captured them in 1995, and the image became one of the most recognized in astronomy. Webb photographed them again in 2022, and the result was a completely different picture. Hubble's version showed the pillars in visible light. The outer surfaces glowed, but the interiors were largely dark and opaque. Webb's infrared vision passed straight through the dust. Inside the pillars, for the first time, hundreds of newly forming stars became visible, embedded deep within the gas columns, shining at infrared wavelengths that dust cannot block. Those stars are in the earliest stages of formation. A region of gas collapses under its own gravity, slowly at first, then faster. As it collapses, it heats. The center grows dense and hot enough to begin nuclear fusion, and a new star ignites. The surrounding gas and dust that did not fall inward forms a disk around the young star, and from that disk, planets may eventually form. This process takes millions of years from initial collapse to stable star. Webb is seeing it at multiple stages simultaneously across the full extent of the pillars. The scale of the Pillars of Creation puts the activity in perspective. The tallest pillar extends roughly 4 to 5 light-years from base to tip. A light-year is roughly 5.9 trillion miles. The pillar is a structure of active star formation, spanning a distance that would take a spacecraft traveling at current human spaceflight speeds tens of millions of years to cross. Inside that structure, stars are igniting. Some of those young stars are already energetic enough to erode the pillar itself. Ultraviolet radiation from newly formed hot stars ionizes and ablates the surrounding gas, carving the irregular, finger-like shapes visible in the Webb image. The pillars are being destroyed by their own contents. Over the next few million years, the structure will disperse. But what Webb's image reveals about the broader process matters beyond the aesthetic. Star formation is happening everywhere. Every galaxy in the universe contains stellar nurseries, regions of gas and dust where gravity is collapsing material into new stars. The Milky Way produces a few solar masses worth of new stars per year on average. Some galaxies, called starburst galaxies, form stars at rates hundreds or thousands of times higher. Webb can observe stellar nurseries in nearby galaxies with enough resolution to study individual star-forming regions, not just average statistics. By comparing nurseries across different galaxies with different ages, metallicities, and environments, astronomers build a detailed picture of how the conditions for star formation change across cosmic history. One finding already emerging from Webb's nearby galaxy observations is that star formation efficiency varies significantly with environment. Dense, metal-rich regions form stars differently from the metal-poor environments of the early universe. This variation affects the predictions for how early galaxies could have built their stellar mass so quickly, connecting stellar nursery physics directly back to the puzzle of massive early galaxies. Stars form, they burn, they die. And what they scatter when they die is not just energy, but the raw material for everything that comes next. Webb watches that cycle playing out across every galaxy it images, and the chemistry those dying stars release is more relevant to our existence than any other process in the universe. Between the stars, space is not empty. It is filled with a diffuse mixture of gas and dust, called the interstellar medium, and Webb has revealed that the chemistry happening inside it is far more complex than earlier measurements suggested. The interstellar medium was known to contain simple molecules: hydrogen gas, carbon monoxide, water ice frozen onto dust grains. These have been detected by radio telescopes and infrared observatories for decades. But the detailed inventory of what floats between stars, the full catalogue of molecular complexity present across the galaxy, was incomplete before Webb. Webb's infrared spectroscopy is sensitive to molecular vibrations in a way that makes it ideal for reading interstellar chemistry. When molecules absorb infrared radiation, they vibrate at frequencies specific to their structure. Those absorption signatures appear as dips in the spectrum of a background star or region, and each pattern of dips is a molecular fingerprint. Using this technique, Webb has detected complex organic molecules in the interstellar medium with a new level of detail. In 2003, a team using Webb data identified a suite of molecules in a dense interstellar cloud, including carbonyl sulfide, methyl cyanide, and various carbon chain molecules, along with simpler ices like carbon dioxide, ammonia, and methanol. Some of these molecules contain the carbon-nitrogen bonds that are fundamental to the chemistry of amino acids, the building blocks of proteins. The presence of these molecules in interstellar space is significant for a specific reason. When a cloud of interstellar gas collapses to form a new star and planetary system, the chemistry present in that cloud gets incorporated into the forming planets. The molecular inventory of the interstellar medium is, in a real sense, the starting chemistry of every new world. If complex organic molecules are widespread in the interstellar medium, they are being delivered to planetary surfaces across the galaxy as a routine part of planetary formation. This does not confirm that life is common. The chemistry present at formation and the conditions required for life to emerge are separate questions. But it does establish that the raw molecular ingredients associated with biological chemistry are distributed widely, present in the interstellar medium of our galaxy, and presumably in the interstellar media of galaxies throughout the observable universe. Webb has also detected polycyclic aromatic hydrocarbons in the interstellar medium, large carbon ring molecules that glow in infrared when illuminated by stellar radiation. These molecules are among the most abundant carbon-bearing species in the galaxy, and they have been found in meteorites that fell to Earth, suggesting a continuous chemical thread connecting interstellar space to the surfaces of rocky bodies. The interstellar medium is a vast, cold, diffuse chemical laboratory, processing molecules across timescales of millions of years between star formation events. Webb is providing the first detailed catalogue of what that laboratory contains, and the complexity of the inventory keeps expanding with each new spectroscopic observation. Every star that forms inherits that chemistry. Every planetary disk condenses it. Every rocky planet accretes it. The molecules that eventually become part of living systems, on a planet somewhere in the galaxy, began their journey drifting silently in the space between stars, illuminated by the infrared light that only Webb can fully read. The chemistry connects the interstellar scale to the planetary scale, and Webb sees both clearly enough to trace the connection. The universe is expanding, every distant galaxy is moving away from us, and the farther away it is, the faster it recedes. That much has been known since the 1920s. What took until 1998 to discover, and what Webb is now measuring with greater precision than ever before, is that the expansion is accelerating. Galaxies are not just moving apart, they are moving apart faster and faster over time. The rate of separation between any two distant points in the universe is increasing. Whatever is driving that acceleration is called dark energy, and it makes up an estimated 68% of everything that exists. The discovery of accelerating expansion came from observations of Type 1a supernovae, the same stellar explosions used in the cosmic distance ladder. In the late 1990s, two independent teams of astronomers were measuring supernova distances at large cosmic distances, expecting to find that gravity was gradually slowing the expansion. Instead, both teams found that distant supernovae were fainter than expected, meaning they were farther away than expected, meaning the universe had expanded more than a constant or decelerating expansion would produce. The expansion was speeding up. Both teams were awarded the Nobel Prize in Physics in 2011 for this discovery. The result has been confirmed by multiple independent methods since then. Webb contributes to this field by improving the precision of supernova distance measurements at large distances, and by refining the Cepheid calibrations that anchor the distance ladder. Better distance measurements at greater cosmic depths help constrain the properties of dark energy over time. Dark energy, in its simplest current model, is described as a cosmological constant, a fixed energy density of empty space that does not change over time. This model, called lambda CDM, where lambda represents the cosmological constant, and CDM stands for cold dark matter, fits the available data well, but it is a description, not an explanation. It says that empty space has a certain energy density. It does not say why. The value of that energy density is itself a profound puzzle. Quantum field theory, the framework that describes fundamental particles and forces, predicts that the vacuum of space should have an energy density based on the contributions of quantum fluctuations from all known fields. The predicted value from quantum field theory is vastly larger than the observed value of dark energy, by a factor that is one of the largest discrepancies between theory and observation in all of physics. There is no agreed resolution to this discrepancy. It is sometimes called the cosmological constant problem, and it has been an open question in theoretical physics since the 1980s. Webb's measurements do not solve the cosmological constant problem, but they are beginning to test whether dark energy truly behaves as a constant over cosmic time, or whether its strength has varied. A dark energy that evolves over time would require a different theoretical explanation than a simple cosmological constant. Some recent analyses of large-scale structure data, including input from Webb observations, suggest hints that dark energy may not be perfectly constant, but the evidence is not yet strong enough to be conclusive. If dark energy is not constant, the future of the universe may be different from the straightforward prediction of continued accelerating expansion. Some models suggest a varying dark energy could eventually reverse, leading to a contraction. Others suggest it could intensify, eventually tearing apart not just galaxy clusters, but stars, planets, and atoms in a scenario called the Big Rip. These outcomes are speculative and distant in cosmic time. The observational data needed to distinguish between them is exactly what Webb is designed to provide. Every large structure in the visible universe sits inside something invisible. Galaxy clusters, each containing hundreds or thousands of galaxies, are surrounded and permeated by halos of dark matter, many times more massive than the visible matter they contain. Webb maps those halos indirectly, and what the maps show is an architecture that governs the entire visible universe from behind the scenes. Dark matter halos are not uniform spheres. They have internal structure. Simulations predict that halos should contain numerous smaller concentrations called subhalos, embedded within the larger halo like bubbles within a larger mass. The galaxies we see are effectively the luminous cores of these dark matter structures. The visible galaxy is the tip. The dark matter halo is the iceberg. For the Milky Way, estimates place the total mass of the dark matter halo at roughly 1 trillion solar masses, while the visible mass of all the stars in the galaxy is a fraction of that. The halo extends far beyond the visible disk of the galaxy, out to distances of several 100,000 light-years, invisible and undetectable, except through its gravitational effects. Webb's gravitational lensing observations provide the most detailed maps of dark matter distributions currently available. By analyzing how background light is distorted by foreground mass, Webb reconstructs where the mass is concentrated in three-dimensional space. These reconstructions show that dark matter is present in the expected large quantities, that it clusters in the way cold dark matter models predict on large scales, and that the boundaries between halos and the surrounding cosmic web are structured rather than uniform. A specific test that Webb enables involves counting the number of dark matter subhalos within a larger halo. Cold dark matter theory predicts a specific abundance of substructure, a certain number of subhalos per unit of halo mass. Prior observations suggested the number of observed satellite galaxies around the Milky Way was smaller than the number of predicted subhalos, a discrepancy called the missing satellites problem. One resolution is that many predicted subhalos never gathered enough gas and stars to form visible galaxies, remaining dark and detectable only gravitationally. Webb's lensing sensitivity, by detecting the perturbations that individual dark matter subhalos produce in gravitationally lensed arcs, provides a new observational handle on subhalo counts that does not depend on those subhalos containing stars. Early results from this technique, applied to lensing systems studied by Webb and its predecessor, the Hubble Space Telescope, are consistent with a population of dark subhalos. Though pinning down exact numbers requires careful statistical analysis, still underway, dark matter's presence is confirmed everywhere Webb looks. Its nature remains unknown. Particle physicists have been searching for dark matter candidates in laboratory experiments for decades. The leading candidates include weakly interacting massive particles, axions, and sterile neutrinos, among others. None have been directly detected in a laboratory setting. Webb does not detect dark matter particles. It detects dark matter's gravity, which is both its strength and its limitation. The maps Webb produces tell us exactly where dark matter is. They say nothing about what it is. The invisible architecture is real, pervasive, and fundamental to the existence of every galaxy, every star, and every planet Webb observes. Its identity remains the largest open question in physics. The direct observation has not yet closed. The largest collisions in the universe are not explosions. They are slow-motion catastrophes unfolding across millions of years, involving systems so massive that the individual galaxies within them are like dust motes in a colliding storm front. Galaxy cluster mergers are the most energetic events in the universe since the Big Bang. When two galaxy clusters collide, each containing hundreds of galaxies and immense quantities of hot gas and dark matter, the interaction releases energy on a scale that dwarfs stellar explosions by many orders of magnitude. Yet because the distances involved are so vast, the process appears nearly still from any human timescale. Webb has observed multiple galaxy cluster mergers, contributing detailed measurements of the stellar populations, gas distributions, and lensing geometries of these systems. One of the most studied merger systems is the Bullet Cluster, located about 3.7 billion light-years away. Though the Bullet Cluster was first studied in detail by the Chandra X-ray Observatory, which revealed hot gas from the two colliding clusters displaced from the bulk of the mass, it has become a cornerstone observation for dark matter science. The Bullet Cluster's significance is this. During the collision, the hot gas in the two clusters, which makes up the bulk of their ordinary matter, interacted electromagnetically and slowed down, ending up concentrated in the center of the collision zone. The dark matter halos, which interact only gravitationally, passed through each other without slowing and moved ahead of the gas. X-ray maps showed where the gas was. Gravitational lensing maps showed where the total mass was. The two did not align. This spatial separation between the ordinary matter and the total mass is direct evidence that the dark matter is real and behaves differently from ordinary matter, exactly as the model predicts. It remains one of the most visually direct confirmations of dark matter's existence and properties. Webb's role in cluster merger science is to study the galaxies within these systems in detail. During a cluster merger, the member galaxies are subjected to intense gravitational interactions, ram pressure from the hot gas, and tidal forces from the overall mass distribution. These interactions strip gas from galaxies, trigger or suppress star formation, and over time transform the galaxy populations within clusters. Webb observations of cluster members in merging systems reveal populations of galaxies at various stages of transformation. Some show active star formation triggered by the pressure of the cluster environment. Others show signs of gas stripping that has cut off their fuel supply. Tracing these transformations allows astronomers to connect the large-scale collision event to the small-scale consequences for individual galaxies within it. The energy released in a major cluster merger, channeled into the hot intracluster gas, can heat that gas to temperatures of hundreds of millions of degrees. That heated gas radiates in X-rays for billions of years after the collision. Webb's infrared observations of the cluster members complement X-ray observations of the gas, combining to produce a more complete picture of the merger's effects. The scale of these events is a useful anchor for understanding what the universe does with its largest structures. Cluster mergers are not exceptional. The cosmic web drives clusters together continuously as the large-scale structure evolves. The Milky Way's own local environment is moving through space, drawn toward a massive concentration of matter that exists at a scale that makes individual cluster mergers look small. The Milky Way is moving. Every galaxy in the local universe is moving, and a significant component of that motion is being pulled towards something. Astronomers call it the Great Attractor, a concentration of mass centered roughly 450 million light-years away, in the direction of the constellations Centaurus and Norma. The gravitational influence of this region affects the motion of hundreds of thousands of galaxies across a volume, hundreds of millions of light-years across, including the Milky Way, the Andromeda Galaxy, and the entire local group. The Great Attractor was first inferred in the 1980s when astronomers studying galaxy velocities noticed that galaxies across a huge region of the sky were moving in a coordinated way that could not be explained by local gravitational sources alone. Something massive was pulling matter toward a specific point. Studying the Great Attractor directly is complicated by its location. It sits behind the plane of the Milky Way, in a region of the sky called the Zone of Avoidance, where the dense gas and dust of our own galaxy's disk blocks optical and even much infrared observation. The obscuring material has made precise mapping of what lies in that direction difficult with most telescopes. Webb's infrared sensitivity, the deepest available, provides some ability to penetrate this obscuration, though the zone of avoidance remains challenging even for Webb at the densest portions. Other wavelengths, particularly radio and X-ray observations, have helped map the mass concentration behind the galactic plane. What lies in the direction of the Great Attractor is actually a complex of structures. The Norma cluster, a massive galaxy cluster, sits close to the attractor's core. Behind it, at even greater distances, lies a supercluster called the Shapley concentration, approximately 650 million light-years away. which is one of the largest concentrations of mass in the observable universe and contributes an additional gravitational pull in the same general direction. The motion of the local group toward this region is real and measurable. Our entire galaxy is moving at several hundred kilometers per second in this direction relative to the cosmic microwave background reference frame. This motion has been ongoing for billions of years. The Great Attractor itself is not a single object. It is a region where the cosmic web produces an unusually dense node, a place where multiple filaments intersect, and mass has accumulated over billions of years of gravitational attraction. The same process that builds individual galaxy clusters operates at this scale, but the concentration is larger. Understanding the full mass distribution responsible for these large-scale flows is an active area of research called peculiar velocity analysis. Webb contributes to this by providing precise distances to galaxies across the relevant sky region, allowing astronomers to separate the component of galaxy motion due to cosmic expansion from the component due to gravitational attraction toward mass concentrations. The picture emerging from this analysis is of a universe whose large-scale gravitational landscape creates rivers of mass flowing along the cosmic web towards dense nodes, with everything in between being pulled, redirected, and incorporated into the growing structure. Our own galaxy is one particle in that flow, moving toward a concentration of mass that has been pulling at us since long before Earth existed. And the concentration pulling at us is large, but somewhere beyond what any telescope can reach. The scale of what exists keeps growing past the point where measurements are possible. Every heavy element that makes up a planet, and every heavy element that makes up a living body, was produced inside a star. It got out through violence. Stars spend most of their lives fusing hydrogen into helium in their cores. For sufficiently massive stars, when the hydrogen runs low, the core contracts, temperatures rise, and fusion of heavier elements begins. Helium fuses into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. At each stage, the star builds a new shell of fusion around the previous one, like a growing set of nested layers. Iron is where the chain stops. Fusing iron does not release energy. It requires energy. When an iron core accumulates to roughly 1.4 times the mass of our stellar neighbor, it can no longer support its own weight. The core collapses in less than a second. The outer layers fall inward, bounce off the newly forming neutron star or black hole at the center, and are blasted outward in a supernova explosion. That explosion seeds the surrounding space with every element the star built throughout its life, plus additional, heavier elements synthesized in the extreme conditions of the explosion itself. The iron, nickel, chromium, oxygen, carbon, and silicon scattered by one supernova become part of the interstellar medium, available to be incorporated into the next generation of stars and planetary systems. Webb observes supernova remnants in nearby galaxies with a resolution and chemical sensitivity that allows detailed mapping of element distributions within the expanding debris clouds. By measuring which elements are present where, astronomers can test models of how supernovae produce and distribute heavy elements. One Webb target is the supernova remnant Cassiopeia A, the remains of a massive star that exploded in our galaxy roughly 340 years ago, as seen from Earth. Webb's infrared imaging of this remnant has revealed detailed structure in the expanding shell, including regions rich in silicon, argon, neon, and iron, each distributed in patterns that reflect the layered interior of the original star and the dynamics of the explosion. Beyond remnants in our own galaxy, Webb observes supernovae in progress in distant galaxies. Each supernova is a flash of light lasting weeks to months, bright enough to briefly outshine its host galaxy in some cases. Webb's sensitivity allows it to detect and characterize supernova at greater distances than prior infrared telescopes, contributing to statistical studies of supernova rates and properties across cosmic time. The supernova rate in a galaxy is linked directly to its star formation rate. High star formation produces many massive stars, and massive stars die as supernova. Webb's ability to measure star formation rates in distant galaxies and connect them to supernova populations across cosmic time provides a continuous record of how the universe has been manufacturing and distributing heavy elements. Throughout its history, the calcium in bones, the iron in blood, the oxygen in every breath, all of it passed through the interior of at least one star and escaped through a supernova before becoming part of the Earth. Webb makes that process visible in real time in other galaxies, watching it happen now as it happened here billions of years ago. The violence of stellar death is the mechanism of chemical creation, and what those deaths create, distributed across billions of years and trillions of stars, is the raw material of the universe's most improbable outcome. The connection between stellar physics and human biology is not metaphorical. It is a chain of real physical events, and Webb is making that chain visible across cosmic time. Every atom in the human body, heavier than hydrogen, was produced inside a star. The hydrogen itself dates to the first minutes after the Big Bang, when protons and neutrons combined in a process called Big Bang nucleosynthesis. Everything else came later, forged in stellar interiors over billions of years. The carbon that forms the backbone of every organic molecule in living cells was produced primarily in stars through a reaction called the triple alpha process, where 3 helium nuclei fuse to form carbon under the extreme pressures and temperatures of stellar cores. The oxygen bound to that carbon in molecules throughout biology was produced in the same stellar environments. Through further fusion of carbon, the nitrogen in amino acids, the phosphorus in DNA, the sulfur in proteins, each element traces back to a specific set of stellar processes at a specific range of stellar masses and ages. Heavier elements, including the iron in hemoglobin and the calcium in bones, were produced primarily in massive stars and dispersed by supernovae. Elements heavier than iron, including copper, zinc, iodine, and others present in biological systems in trace quantities, were produced in neutron star mergers, events where 2 neutron stars spiral together and collide, briefly producing the conditions necessary for the rapid neutron capture process that builds the heaviest nuclei. Webb has observed the aftermath of neutron star mergers through their infrared signatures. When 2 neutron stars collide, the event produces a gravitational wave signal detectable by instruments like the Laser Interferometer Gravitational Wave Observatory, and simultaneously an electromagnetic transient called a kilonova. Kilonovae glow in infrared as the newly synthesized heavy elements cool and radiate. Webb's sensitivity to infrared makes it an important tool for studying kilonovae and confirming the heavy element production that theory predicts. The first confirmed kilonova with detailed spectroscopic follow-up, associated with a gravitational wave event detected in 2017, showed clear signatures of strontium and other R-process elements in its spectrum, providing direct observational confirmation that neutron star mergers produce heavy elements. Webb's ability to detect kilonovae in distant galaxies and to measure the spectra of their heavy element products extends this confirmation across cosmic time. By observing kilonova rates and yields at different epochs in the universe's history, astronomers can build an account of when different heavy elements became available in the universe, and in what quantities. That account connects directly to the timing of when chemistry capable of supporting complex molecules became possible. Carbon chemistry requires carbon. Carbon requires stars. The first stars that produced and dispersed carbon were massive, short-lived population 2 stars that formed in the early universe and died quickly, seeding the next generation's birth clouds. By roughly 10 billion years ago, the universe had accumulated enough heavy elements in enough places to begin producing the kind of rocky, chemically rich planetary systems necessary for complex chemistry. The solar system formed about 4.6 billion years ago, incorporating heavy elements from multiple generations of stellar death. Webb photographs that entire history: early galaxies with metal-poor stars, later galaxies with richer chemical environments, stellar nurseries incorporating heavy elements into new planetary systems. The chain from Big Bang to biology runs through every image Webb produces. In 22,000, astronomers confirmed the distance to a galaxy called JWST 13-0, identified in data from the James Webb Space Telescope's JWST survey, the JWST Advanced Deep Extragalactic Survey. Its light left the galaxy when the universe was approximately 325 million years old. 325 million years after the Big Bang, the universe is 13.8 billion years old. This galaxy existed when the cosmos had completed less than 3% of its current lifespan. It existed before the Milky Way, before the solar system, before Earth, before any rocky planet in our neighborhood had any reason to exist. And it already contained stars. That fact carries weight beyond the number. A galaxy requires a formation history. Gas must collapse. Stars must ignite. The galaxy must accumulate enough mass to be detectable. The existence of a structured, star-containing galaxy at 325 million years means the first stars formed even earlier. The first gas collapses happened even earlier. The first density fluctuations that seeded structure were already working from the very first moments of the universe's existence. The light from this galaxy has been traveling for over 13 billion years to reach Webb's mirror. The photons that carry its image were emitted before the Earth existed, before the solar system existed, before the Milky Way had assembled its spiral arms. They traveled through a universe that built and destroyed entire generations of stars in the time they spent crossing space. When they arrived at Webb, they had been stretched by the expansion of the universe from ultraviolet wavelengths, the wavelengths at which they were originally emitted, to infrared wavelengths, the only wavelengths Webb can detect at this extreme distance. That stretching, called redshift, is how Webb identifies the distances of the farthest objects. The more stretched the light, the earlier in the universe's history the source existed. JWST 13.0 is not the final word. Webb's ongoing surveys continue to push the confirmed distance record further. In 2023 and 2024, candidate galaxies at even greater distances were identified in Webb data, with some potentially existing at redshifts corresponding to the universe at 200 million years of age or less. Spectroscopic confirmation of these candidates is ongoing. The practical implication of finding formed galaxies this early is that the universe's first chapter, the transition from the nearly smooth post-Big Bang state to the first recognizable cosmic structures, was compressed into a shorter window than the standard model comfortably accommodates. Structure formation was efficient, fast, and began producing detectable galaxies earlier than calibrated simulations predicted. This is not a crisis for cosmology. Models are being adjusted, simulations refined, initial conditions reconsidered. Science proceeds through exactly this kind of pressure from new data, but the direction of pressure is consistent. Every confirmed record-breaking distant galaxy Webb finds is another data point showing that the early universe was more active and more productive than the pre-Webb picture suggested. The farthest object we have ever confirmed seeing is already a galaxy, already assembled, already making stars, already chemically enriching its surroundings, already doing the work of a cosmos that had arrived fully operational before our own galaxy had been born. The observable universe has a boundary. It is not a wall. There is no surface to reach. It is simply the distance beyond which light has not had time to reach us since the universe began. Light travels at a fixed speed. The universe has a finite age. Multiplying one by the other gives a maximum distance from which any signal can have arrived. The observable universe, the sphere of space from which light could in principle have reached us by now, has a radius of roughly 46 billion light-years. That number is larger than the age of the universe times the speed of light, which would be about 13.8 billion light-years, because the universe has been expanding the whole time light was traveling. Space itself stretched during the journey, carrying distant objects to greater separations than the light travel time alone would suggest. Beyond 46 billion light-years, space exists. Matter almost certainly exists. Structure almost certainly exists. But no signal from those regions can have reached us yet. We cannot see them, measure them, or communicate with them. They are causally disconnected from us. Nothing that happens there can currently affect us, and nothing here can currently affect them. This boundary is called the cosmic horizon, and it is one of the most vertiginous facts in physics. The universe almost certainly extends far beyond what any instrument, including Webb, will ever access. How far beyond is unknown, possibly infinite. Webb's contribution to this picture is not to push the cosmic horizon outward. No telescope can do that. The horizon is set by physics, not by instrument sensitivity. What Webb does is populate the region near the horizon with real observations, giving us confirmed galaxies approaching the edge of what is accessible and revealing what the universe looked like in that earliest accessible era. The structure of the universe near the cosmic horizon, in those first few 100 million years, is a region where the standard model's predictions can be tested against real data. Webb is the first instrument capable of performing those tests in detail. Every confirmed early galaxy is a data point in a region that was previously accessible only through theoretical extrapolation. There is a further implication of the cosmic horizon that connects to the accelerating expansion discussed earlier. Because the universe is expanding at an accelerating rate, the cosmic horizon is not static. Over time, objects that are currently near the edge of our observable universe will eventually recede faster than light can cross the growing gap. They will become permanently unreachable, and their light will become permanently undetectable. The universe we can observe is therefore shrinking in a specific sense, not in physical size, but in the number of objects that will ever be accessible to future observers. Galaxies that are currently near the edge of observability will eventually pass beyond it permanently. Future civilizations, billions of years from now, will observe a universe that appears smaller, with fewer visible galaxies and less information accessible than the universe we can observe today. Webb is observing near the maximum possible depth available to any observer at this moment in cosmic history. The window is real, limited, and temporary. What we learn by looking through it now is information that will eventually become inaccessible as the universe continues to expand. The scale revealed by Webb is not just large, it is partially and permanently hidden, with more disappearing beyond the accessible boundary all the time. The observable universe is everything inside the cosmic horizon. It spans roughly 93 billion light-years across. It contains an estimated 2 trillion galaxies, hundreds of billions of trillions of stars, and a number of planets too large for any analogy to convey. That is the accessible portion. Beyond that boundary lies the rest of the universe, the part that physics says almost certainly exists, and that no observation will ever reach. The size of the full universe is genuinely unknown. Current cosmological models constrain it, but cannot determine it precisely. Measurements of the cosmic microwave background by the Planck satellite show that the geometry of the observable universe is flat, or extremely close to flat, within the precision of current measurements. In a universe with flat geometry, the total universe is either infinite or vastly larger than the observable portion. Some models that fit the available data suggest the full universe could be at least 250 times larger than the observable portion in linear scale, meaning enormously larger in volume. Others allow for a universe that is infinite in extent. The concept of inflation, the theoretical period of exponentially rapid expansion in the universe's first fraction of a second, predicts that the full universe is far larger than the observable portion. Inflation takes quantum-scale regions and expands them to cosmic scales in an almost immeasurably short time. If inflation occurred, and the evidence from the cosmic microwave background's pattern of fluctuations strongly supports the occurrence of something like it, then the universe beyond our horizon is not just slightly larger, it is incomprehensibly larger. Some inflationary models predict that inflation produced not one, but many distinct regions of space, each with potentially different physical conditions, in a scenario called eternal inflation. This is speculative territory, firmly at the theoretical frontier, and not directly testable with current observations. Webb cannot observe beyond the cosmic horizon, and no instrument ever will. What Webb does is sharpen our understanding of the observable portion, so precisely that it constrains the models that describe what lies beyond. Every measurement of the Hubble constant, every confirmed early galaxy distance, every dark energy constraint Webb produces, feeds into the cosmological models that make predictions about the full universe's structure. Better measurements of the observable produce better constraints on the unobservable. The observable universe itself, 13.8 billion years old and 93 billion light-years across, is already a scale that defeats human comprehension. The acknowledgement that it represents only a fraction, possibly an infinitesimal fraction, of a larger whole adds a layer of epistemic humility to every Webb observation. What Webb photographs is real, confirmed and precisely measured. It is also a sample, a slice, a window. The universe behind that window is larger than the window by a margin that cannot be determined, and may have no determined value at all. Every Webb image, then, is both a triumph of observation and a reminder of what observation cannot reach. The 10,000 galaxies in a grain of sand of sky represent a tiny portion of the observable universe, which represents an unknown fraction of the full universe. The numbers do not resolve into anything manageable. They keep expanding as the measurement precision improves. Webb does not make the universe smaller and more comprehensible. It makes the visible portion of a larger unknown larger than it was before. To see the oldest light in the universe, Webb had to become one of the coldest objects in the solar system. The engineering required to achieve that is as extreme in its own domain as the cosmic scales Webb measures are in theirs. Webb's scientific instruments operate at a temperature of around negative 448 degrees Fahrenheit. For reference, the average temperature of deep space, far from any star or heat source, is around negative 455 degrees Fahrenheit, about 3 degrees above absolute zero, the theoretical minimum temperature, where all thermal motion stops. Webb's detectors operate within a few degrees of that absolute floor. That temperature is not just a curiosity, it is a scientific necessity. Webb's primary mission involves detecting infrared radiation, which is electromagnetic radiation in the heat range of the spectrum. Every object warmer than absolute zero emits infrared radiation. If Webb's detectors were warm, the telescope would be blinded by its own thermal emission, unable to distinguish the faint infrared signals from ancient galaxies from the overwhelming noise of its own heat. Achieving that operating temperature required a multi-layered approach. Webb carries a sunshield the size of a tennis court, made of 5 layers of a specially coated material called Kapton, each layer thinner than a human hair. The sunshield blocks the thermal radiation from the Earth, Moon, and the star our planet orbits. On the cold side of that shield In permanent shadow, the temperature drops to the level Webb's instruments require. The mid-infrared instrument, called MIRI, requires an even lower temperature than the other instruments, around negative 449.7 degrees Fahrenheit, to detect the longer infrared wavelengths it is designed for. Achieving this required an active cryocooler, a mechanical refrigeration system built into the telescope that pumps heat away from MIRI's detectors. This cryocooler was one of the most technically demanding components of the mission. It operates in space at a location 1 million miles from Earth and must function without maintenance for the telescope's planned 10 to 20-year operational lifetime. Webb launched on December 25, 2021, folded into the Ariane 5 rocket like an origami structure, because its mirror and sunshield were too large to fit inside any rocket fairing in their operational configuration. The unfolding sequence after launch took 2 weeks, with each step critical and irreversible. There were over 300 single-point failures that could have ended the mission. All of them were navigated successfully. Webb sits at a gravitational balance point called the second Lagrange point, 1 million miles from Earth, in the direction away from the star our planet orbits. At this point, the gravitational pulls of Earth and the star combine to keep Webb in a stable orbit around the second Lagrange point itself, facing permanently away from the heat sources it needs to avoid. The precision required to build, launch, and operate Webb successfully puts the engineering scale of the mission in conversation with the scientific scale of what it observes. To measure a universe billions of light years across, humans built a machine 1 million miles away and cooled it to within degrees of absolute zero. That machine is working. It is currently operational, sending data, and the scientific community has estimated that the volume of scientifically important results it will produce over its operational lifetime will keep astronomers engaged for decades beyond the mission's end. The James Webb Space Telescope's primary mirror spans 21 feet across, made of 18 individual hexagonal segments. Each segment is made of beryllium, a lightweight metal chosen for its stiffness at cryogenic temperatures. Each segment is coated with a thin layer of gold, which reflects infrared light more efficiently than other common mirror coatings. Beryllium was chosen deliberately. At the temperatures where Webb operates, many materials become brittle or change shape. Beryllium maintains its structural integrity and, critically, its precise shape, even as temperatures drop to near absolute zero. A mirror that distorts in the cold would produce blurred or inaccurate images, rendering the telescope scientifically useless. The polishing precision required for each segment is among the tightest tolerances ever achieved in manufacturing. Surface irregularities had to be kept below 100 nanometers, where a nanometer is 1 billionth of a meter. Human hair is roughly 80,000 nanometers wide. The mirror surfaces had to be accurate to a fraction of a wavelength of the infrared light they were designed to reflect. After launch, the 18 mirror segments required alignment. Each segment can be moved with actuators, tiny motorized mechanisms that adjust the segment's position and tilt with nanometer-scale precision. Over the weeks following launch, ground controllers sent commands to gradually align all 18 segments into a single coherent mirror. The alignment was confirmed in stages, starting with images of a single star split into 18 copies by the misaligned segments, and ending with all 18 copies merged into one sharp point of light. The result exceeded pre-launch expectations. Webb's optical performance, measured against the design specifications, came in better than required. The telescope can produce images sharper and more sensitive than the conservative engineering margins predicted. What that sharpness allows is the separation of closely spaced objects that would blur together in any prior infrared telescope. Individual stars in crowded galactic centers, multiple gravitationally lensed images of background galaxies, separated by fractions of an arcsecond on the sky, the detailed structure of gas and dust clouds in stellar nurseries, subtle chemical gradients across the faces of nearby galaxies. Webb's sensitivity, the faintest signal it can detect, is a consequence of both mirror size and operating temperature. A larger mirror collects more photons per unit time. Lower detector temperatures mean lower noise, allowing fainter signals to rise above the background. The combination of a large, cold, precisely shaped mirror and sensitive infrared detectors produces a telescope capable of detecting a single candle at the distance of the moon, according to one engineering description of its light-gathering capability. That sensitivity is what makes everything in this video possible. The early galaxies, the exoplanet atmospheres, the stellar nurseries, the gravitational lensing maps, the quasar spectra from the universe's first billion years. All of it depends on a machine precise enough to catch photons that have been traveling for over 13 billion years and arrive carrying the faint chemical signatures of objects that existed before our planet was born. The engineering challenge of building Webb and the scientific challenge of understanding what it finds are both extensions of the same human impulse, to see further than seemed possible, and to accept the full scale of what is revealed. Webb is operating in an era of deep tension in cosmology. Multiple independent measurements of the universe's structure and composition are producing results that do not all agree with each other, or with the standard model's predictions, and the precision of those measurements is now high enough that the disagreements cannot easily be dismissed as measurement error. The Hubble tension, discussed earlier, is the most prominent of these. But a second tension, less publicized and equally unresolved, is adding pressure from a different direction. Cosmologists measure how much structure has clumped in the universe, how concentrated matter is relative to a perfectly smooth distribution, using a parameter called sigma 8. The cosmic microwave background measurements, analyzed using the standard model, predict a certain value for sigma 8, meaning a certain degree of clumpiness in the matter distribution today. Direct measurements of the matter distribution today, using techniques like weak gravitational lensing surveys of large numbers of galaxies across the sky, have found a sigma 8 value slightly lower than the prediction. The universe appears to be slightly less clumped than the early universe data predicts it should be. The discrepancy is not enormous. It sits at roughly 2 to 3 sigma of statistical significance, meaning it is real enough to study seriously, but not yet definitive enough to declare the model broken. However, it has persisted across multiple independent surveys, including data from projects like the Kilo Degree Survey and the Dark Energy Survey, and it has not resolved as precision improved. Webb contributes to this problem by providing precise measurements of early galaxy clustering, galaxy cluster masses, and large-scale structure at intermediate redshifts. Every data point Webb adds to the structural map of the universe either narrows or maintains the discrepancy with the prediction. One proposed explanation involves the behavior of dark matter on small scales. The standard cold dark matter model, where dark matter particles move slowly and cluster strongly, predicts a certain clumpiness. Some alternative dark matter models, including warm dark matter, where particles move faster and resist small-scale clumping, or self-interacting dark matter, where dark matter particles interact with each other, predict slightly less small-scale structure. If dark matter is not perfectly cold, the sigma 8 tension might ease. Another proposal involves how massive neutrinos affect structure formation. Neutrinos are lightweight particles that travel at nearly the speed of light and smooth out small-scale structure by streaming freely through forming over densities. If the total mass of neutrinos is on the higher end of current experimental limits, their smoothing effect could reduce the predicted clumpiness, reducing sigma 8 from the standard prediction toward the observed value. Neither explanation is confirmed. Both are being tested against data that Webb and contemporaneous surveys are producing. The resolution, when it comes, will either be a refinement of the standard model's parameters, or a sign that one of its fundamental ingredients, dark matter, dark energy, or neutrino properties, differs from current assumptions. What makes this moment in cosmology significant is that two independent tensions are pointing toward the same conclusion. The standard model works remarkably well, but something within it, not yet identified, is slightly off. Webb is generating the measurement precision needed to identify exactly where. Webb has been scientifically operational since July 2002. In the roughly 3 years since, it has produced a volume of data that astronomers describe as transformative for multiple fields simultaneously. The full scientific output of the mission is expected to extend decades beyond its operational lifetime. The sheer number of confirmed results already in the published literature spans areas that had previously been studied by entirely separate communities with separate instruments. Early universe galaxy formation, exoplanet atmospheric chemistry, stellar nursery physics, gravitational lensing dark matter maps, quasar host galaxies, kilonova spectroscopy, supernova remnant chemistry. Each of these fields received significant contributions from Webb in its first few years of operation. The rate of published papers using Webb data has been high. Within the first year of science operations, hundreds of refereed scientific papers using Webb observations appeared in journals. The pace has continued, with Webb data feeding into research programs that span the full range of modern astrophysics. Part of what makes Webb's output unusual is its simultaneity of scale. Prior telescopes were often optimized for specific distance ranges or object types. Hubble excelled at visible light observations of objects, from nearby star systems to moderately distant galaxies. Spitzer, An earlier infrared space telescope covered infrared wavelengths, but with a much smaller mirror and lower sensitivity. Webb combines the aperture needed to see extremely faint, distant objects with the infrared wavelength coverage needed to observe everything from cold nearby objects to the redshifted light of the early universe in a single instrument suite. That simultaneous coverage means that findings in one domain often connect to findings in another. The chemical abundances Webb measures in the interstellar medium connect to the atmospheric compositions it detects on exoplanets. The early galaxy mass measurements connect to the black hole growth timeline problem. The gravitational lensing dark matter maps connect to the sigma-8 tension. Webb's observations are cross-linked in ways that prior telescope data rarely was, because prior telescopes rarely covered the full range of scales. Webb also operates as a community resource. The Space Telescope Science Institute, which manages Webb operations, allocates observing time through a competitive proposal process open to researchers globally. Early release observations were made immediately public, allowing the worldwide astronomical community to begin analyzing Webb data from the moment it arrived. The archive of Webb data grows continuously and remains publicly accessible. One practical measure of Webb's impact is the number of pre-launch assumptions it has already forced researchers to revise. The galaxy mass-to-age problem, the Hubble tension made more precise, the chemistry of exoplanet atmospheres, detectable for the first time, the detailed structure of stellar nurseries revealed behind dust, the sigma-8 tension maintained at higher precision. Each of these represents a pre-Webb expectation that Webb's data has either confirmed, refined, or put under active pressure. The telescope launched with a fuel reserve sufficient for a minimum 10-year mission, and possibly 20 years or more of operation, depending on fuel consumption. Estimates after launch suggested the fuel was used so efficiently during orbital insertion that the mission lifetime could extend well beyond the original design target. Every additional year of operation means another year of data at the precision and depth that only Webb currently provides. Webb has measured a universe of 2 trillion galaxies. It has photographed light from galaxies that existed 325 million years after the Big Bang. It has found black holes billions of times more massive than stellar remnants growing faster than current theory allows. It has detected the chemistry of worlds 40 light-years away and the structure of voids 300 million light-years across. It has sharpened 2 major tensions in the standard cosmological model and revealed a universe more crowded, more rapidly structured, and more chemically active in its early epochs than the pre-Webb picture captured. What does that scale mean for anything beyond the numbers? The first thing it means for science is that the standard cosmological model is being stress-tested with a precision that prior instruments could not achieve. The model survives the pressure. It is the most successful description of the universe's large-scale properties ever constructed. But it is showing seams in the places where its predictions can now be tested most precisely. And those seams point towards something not yet included in the equations. The Hubble tension is real and unresolved. The sigma-8 tension is real and unresolved. The early massive galaxies are real and difficult to explain in the available formation time. The early supermassive black holes are real, and their growth timeline challenges current accretion models. These are not dismissed as errors. They are active research frontiers, being worked on by large teams using Webb data alongside other observatories. The second thing the scale means is a recalibration of what constitutes a meaningful address in the universe. Earth is one planet around one star in the Milky Way, one of 2 trillion confirmed galaxies in the observable universe, which is itself likely a fraction of the full universe. The statistical weight of that address is vanishingly small. That fact has been acknowledged in cosmology since the Copernican revolution, but Webb makes it concrete in a way that prior instruments, with their low resolution and smaller sample sizes, could only gesture toward. The third thing is specific to the question of life. Webb's atmospheric detections on exoplanets, its mapping of organic chemistry in the interstellar medium, its statistical contribution to the count of potentially habitable worlds. All of these observations move the question of life in the universe from philosophical speculation toward empirical constraint. No biosignature has been confirmed. The search is active. Webb is the first instrument with the sensitivity to find one, if it is detectable. What Webb has not found, what no observation can provide, is a limit to the scale. Every improvement in measurement depth has revealed more structure, more galaxies, more chemical complexity, more physical tension with simple models. The universe observed with greater precision does not simplify. It deepens. Scientists who work with Webb data regularly describe the experience of processing its images and spectra as cognitively destabilizing. The scale is real, the measurements are confirmed, The universe is this large, this old, this full, and this far from simple. Webb revealed something genuinely hard to hold, not a mystery in the comfortable sense of a puzzle waiting for a clean solution, but a scale and a depth that keeps growing as the precision of observation improves.